Hello, everybody, and welcome back to Calculus 3 at Frederick Community College. My name is Val Lockman. I'm the instructor for this class, and in this video, I will discuss two main objectives, graphs and level curves of functions of two variables. Now, before we do this, let me just go ahead and remind you what we've done in algebra, pre-calculus, and our previous classes, where we talked about domains of functions of one variable. So for example, if we take a look at a polynomial function, something like 2x squared minus 1, we know the graph of this function is a parabola, right, that opens up. We know that the domain of this function is all real numbers, so we can denote it as an interval from negative infinity to infinity, or we can also say the entire real line. Okay. What about function f of x, which looks like 1 over x, right? So this is the reciprocal function. Okay, what does that look like? Okay, we know the graph of this function looks something like this. Okay, we have some asymptotic behavior as we get close to 0. So in this case, we would say x is not equal to 0. Or if you wanted to use interval notation, you would say from negative infinity to 0, excluding the 0, right? And then from 0 to positive infinity. Okay, let's see. What else? What about a logarithmic function? Something like natural log of x plus 4. Okay, so this is a transformed log function. Okay, we know that the expression inside the parentheses needs to be strictly greater than 0. So from here, we would say x is greater than negative 4, right? Okay, and then the domain of this function would start at negative 4, and we're not including it, and go to the right. Okay, so in the interval notation, you would say the domain is from negative 4 to positive infinity. Okay, so if you take a look at these simple examples, you will see that the domain of a function of one variable is part of the x-axis, right? Okay, so it's a line segment, either bounded or unbounded, all right? But it is part of just R. Now we're going to shift our focus to functions of two variables. Okay, how we're going to make this shift, right? We're going in multiple dimensions. Now we have two variables, okay, x and y. So let's go ahead and take a look at these problems. Okay, the first problem that I'm looking at is a function x over y. So on the right part of the notes, you see that I have a sketch. Okay, I have a plot that I used Wolfram Alpha to come up with a picture of this surface, right? So now my graphs are not just curves, they are surfaces. But what is the domain is going to look like? The main difference is that now our domain will be um, part of R2, okay? All right, so it will be a region, not necessarily just a straight line, right? Or a portion of R, okay? So let's take a look. What do we have here? X over Y. So we don't want division by 0, right? We don't want 0 in the denominator, so this is Y is not equal to 0. In this case, what does that mean? All points in XY plane such that the y coordinates is 0, but that's the entire x-axis, right? Okay, so let's take a look at our xy plane. So let's say this is our xy plane. We want to exclude all points where y is equal to 0. So that's this line right here. I'm going to exclude it by highlighting in red. So part of the domain for this function, what is it? Everything that's not on that line, right? So I'm highlighting my domain in green, okay? All points, all ordered pairs, x, y, except those where y is equal to 0. And here on the graph, let me go ahead and highlight it here. It is this portion right here. Okay, you can see that what's happening, we have our surface kind of bending, right, and going up to infinity and down to infinity, depending on which region of the plane we're looking at. Okay, but you can see that we have a similar um, asymptotic behavior, except we're now working with a surface, right? So in a way, you can think about this sheet of paper now going up to infinity and down to infinity, um, depending on where we're looking at it, but along that line, and there it is, you see y is equal to 0 right here, we do not have an actual surface, okay? So the portion of the domain for this function includes all points except those on the x-axis. All right, let's see. If you wanted to check this, you would go to Wolfram Alpha, and what you would do, you would plug in this, you would type it into the box, plot 3D, and just like that, you can say z is equal to x over y, and it will spit out the answer for you, so you will see that sketch right there. Okay, so that's our first example. Let's take a look at the next one. Here I have a function 1 over x squared minus y squared. Okay, once again, we do not want this expression in the denominator to be 0, so that's not equal to 0. Okay, that means what? X squared is not equal to y squared. Okay, which means x is not equal to y or negative y, right? If we were to get rid of that square, don't forget the plus or minus, right? Okay, what does that look like? X is equal to y and x is equal to negative y. Well, let's just make our xy plane. Okay, x is equal to y, it's this identity line, right? Okay, x is equal to negative y is this line right here. So this is what we want to exclude from the domain. Okay, stuff in red, that's gone. And now I'm going to highlight the rest of our 2 to indicate this portion is fine. This is where my function is defined. Okay, and you can clearly see on the graph on the right portion of the notes, okay, that we have asymptotic behavior around those lines. Okay, the graph, the surface does not exist for those values of x and y, where they're either the same or they're negatives of each other. Okay, so this is a nice visual representation of what a domain of a function of 2 variables will look like. Okay, let's take a look at the next example. Okay, this one is fun. Here we're dealing with log function. Okay, so natural log of this expression x squared minus y. Okay, what do we do with that one? Okay, so we take our expression inside the function and we want to set it strictly greater than 0, right? Okay, so once that happens, this is equivalent to x greater than y, okay? Or if it's easier for you to view it this way, this is y is less than x squared, okay? Let's take a look at what this represents in R2, okay? Y is equal to x squared. We know that's a parabola, right? Okay, I'm gonna make that in a dashed line like this. Okay, so that is our y is equal to x squared. Now we have y is less than x squared, which means we're not including the points on the actual parabola. But which way are we going to shade our plane? Now the plane is split in 2 portions, right? Okay, which way? We can always test a point. So for example, let's pick a point over here. This could be something like 0, 4, right? Okay, is that true? So 0, is that less than 4 squared? No, that's false. So that point does not satisfy this inequality, right? Okay, we can pick a point, let's say right here. right? This could be something like, let's go with 1 and negative 1. Okay, is that true? Negative 1, is that less than 1 squared? Yes. Okay, and that does not have to be these particular points. It could be anything. But now we know that the portion of the plane, that's the domain for this function, is the one below the parabola. Okay, so I'm going to highlight everything that's in red that's not part of the domain. So the entire curve, and then this portion right here that's not the domain. Okay, and now you can view the graph of the actual um, function, the surface. And that one is not really easy to visualize, but you can kind of see how there's that shape of the parabola, right? And the surface is sitting above the part that's equivalent to the green shaded region that we have in our picture. Okay, and Wolfram Alpha doesn't allow you to rotate these images easily. Okay, so if you find a different graphing utility that lets you do this rotation and maybe scaling and adjusting of the axis, let me know. Okay, but this one was the best that I found that's easily available to kind of play with and view these images. All right, let's take a look at one more example. Okay, so here I have a function f of x is equal to 1 over square root of this expression x squared plus y squared minus 25. Okay, and again on the right you can see what the image of portion of that surface looks like. Okay, so we're going to take our expression x squared plus y squared minus 25, root of that. We don't want this to be 0, right? Okay, but we also want this expression to be strictly greater than 0. So 0 is in the denominator, that's no good, okay? Also, the expression under the radical, that needs to be positive, okay? So that means what? It's x squared plus y squared greater than 25. And now you might be recognizing what this inequality describing, okay? If we were to look at the left part of this inequality, that should look really familiar, right? So this is x squared plus y squared greater than 5 squared. This is a circle of radius 5 centered at the origin, but we want stuff that's outside it, right? Okay, which means the actual circle and what's inside, that's not part of the domain. Okay, what is part of the domain is everything outside. Okay, so to stay consistent, I'm shading my domain in green. Okay, and you can see what's happening on the right. Okay, you have your surface that has this asymptotic behavior around the circle, and it's defined for everything that's equivalent to the green portion of our sketch, right? Okay, and then it's undefined for everything inside that circle. All right, so now you can see the analog of computing the domain, right? Determining domains, graphing them, okay? It's just a little bit more involved because now our original domain is the entire R2, right? And what we can exclude from R2, that really depends on the function that you're dealing with, okay? So that's your domains of functions of two variables. Okay, couple of example here. And there's many things that we could ask, but in general, it's a good idea to know things like what's the domain of a trig function, what's the domain of exponential, logarithmic, polynomial, rational functions. Those, that family of functions that we've discussed in pre-calculus, algebra, and calculus 1 and 2. Okay, let's go ahead and take a look at the next objective, and this one is dealing with level curves. Okay, level curves, or also we can refer to them as contour map. Okay, what it is is a way to visualize the behavior of a function by kind of looking at portions of its graph in a lower dimension. And once we take a look at some examples, this will make a lot more sense. Okay, but basically the idea is that we're going to pick some values for z. Okay, so pick some values for z for our function. Okay, and what I mean by that, actual numbers, and we're going to set our function equal to those numbers. You can think about it as a plane, right? So z is equal to 2. What is that? It's just a plane that's parallel to xy plane, and it's shifted 2 units up. Now, if we set that equal to our surface, then what we're really finding is the cross sections of the plane and that surface. And what they will be looking like, they will be curves. Okay, so let's just go ahead and take a look at some examples, and it will make a lot more sense once we do these by hand and also then compare our work with Wolfram Alpha. Okay, so let's take a look at this function. Z is equal to x minus y. What I'm going to do, I'm going to make a table, okay, where I will have 2 columns. Okay, and I'm going to pick values for z, so I'm going to just pick 0, 1, 2, 3, and 4. Okay, this should be enough to give me an idea of what my graph is going to look like. And then I'm going to set my actual function, so this is x minus y squared equal to those values. Okay, now you might be asking, how do I know how many to pick? And typically 4, 5, or 6, that's a good number to get a general idea of what the surface is looking like. Okay, and then also we should be worried a little bit about the domain and the range of these functions. But in this case, let's see, we have z is equal to this polynomial function, right? Which means the domain is anything. Okay, so the domain is all of R2 because that's a polynomial function. Polynomials are defined for everything. Okay, so we don't have to worry about too many restrictions here. All right, let's take a look. So what do we get? Now I'm going to set x minus y squared is equal to 0, x minus y squared is equal to 1, and I'm just going to set my function to these values right here. Okay, now I would like to see what that looks like. Okay, these are now curves. Okay, so now these are curves. Think about it kind of like bringing it down 1 dimension or projecting onto xy plane. So this one is x is equal to y squared. This one is x is equal to y squared plus 1, and so forth. So you can see that I'm just going to rewrite these as a function of y. Okay, and they're simple enough that we should be able to figure out what the sketches look like, right? So this is y squared plus 4. That's my last one. Okay, so now I'm going to make a contour map or level curves map. Okay, this is my x, this is my y, and my first curve is x is equal to y squared. Okay, I know what that is. That is a parabola that opens this way, right? Okay, that is the cross section of my surface with z is equal to 0. So now I'm going to mark this with z null is equal to 0. So in a way, I'm saying this curve right here lives in the xy plane. Okay, that's where it's located. Okay, now let's see, what about next one? This next curve is y squared plus 1. Well, I know what that is. Now, this is still that same parabola, except now it's shifted 1 unit to the right. Okay. All right. So now this curve, I'm going to mark it with z null is equal to 1. So what I should now visualize is that, oh, this curve is really sitting 1 unit above xy plane. Okay, it's really elevated. Okay, and then we can do the rest of them. So x is equal to y squared plus 2. Okay, it's this curve right here. So that's z null is equal to 2. And then we have 3 and 4, right? So they're all this parabolas that have the same shape, they're just shifted. Okay, I'm going to mark them all with the corresponding value. So z null, this one is 3, and this one right here is 4. Okay, and that should give me enough information to have this visual representation of what that looks like. Okay, so let me go ahead and kind of give you a quick sketch of what really you should try to visualize as you sketch these. And I know it's a little challenging at first, but really now I'm going to kind of map these same curves in 3 space. So if this is my, let's see, how is that going to look like? Yeah, this is going to be my X, and this is going to be Y, and this is Z. So now what's happening here? My first curve is truly in XY plane, but my second curve is 2 units up, okay? And then the third one is 2 units up. The third one is 2 units up. The first one is 1 unit up, right? So this one is in XY plane. This one is 1 unit up, and so forth, okay? That is what the picture that you should kind of have in your mind as you're making these curves. Okay, so level curves are just a way for us to visualize a complicated object, or really just kind of look at its behavior, right? Because a lot of times we don't need to see the entire surface if we just want to know some of its behavior. Okay, and another way to think about it is that level curves are kind of like a skeleton. Okay, it's missing some information, but it's telling us in general what that shape of that surface is going to look like. Okay, so the key components are here of what? Okay, so we're going to pick values for um, our z, right? Set them equal to the function, then solve either for x or y. And sometimes we won't be able to solve for x or y. We just will recognize that, oh, this is an equation, let's say, of a circle or maybe an ellipse. And then we recognize the curves, and then we map them out and mark them with the corresponding z values. And you keep in mind those values are representing heights, right? So that's your general idea of level curves. Let's take a look at the next example. Okay, so here I have z is equal to square root of x squared plus 4y squared. So here I want to go ahead and take a moment to indicate that the range of z is greater than or equal to 0, right? Okay, because we have the square root of function here, square root of a polynomial. The expression inside is always positive, so that's great, unless x and y are both 0, so then we get 0, right? But for this particular function, okay, we notice that z is greater than or equal to 0, which that means what? For the values that we're going to pick, we're only going to pick values that are greater than or equal to 0. Okay, let's go ahead and come up with a table. So z null in the left column, okay, and then here I'm going to say the square root of x squared plus 4y squared is equal to z null. Okay, I'm going to pick 4 values here. That should be enough for me to get a general idea of what my surface is going to look like. So this would be square root x squared plus 4y squared is equal to 0. Okay, and then I'm just gonna equal this function to all of my numbers. Okay, so now what? We would like to get rid of that square root on the left side, so it makes sense to square each side. Okay, so here we get 0, we get 1. For the next one, next curve, we get 4, and then this last curve, we get 9. Okay, so what are these? Okay, now these are curves, right? These are curves in our xy plane, and they're just ellipses. Okay, well, one of them is the very boring level curve. The first one is just the point 0, 0. That's the origin. Okay, and it makes sense because you can say, okay, what is the smallest value that z function will take here? 0, right? Okay, when x and y are both 0. So start thinking about it. Okay, that's my surface. That's where it kind of starts growing from. Okay, what about the next one? So that's going to be an ellipse, and it's going to be bigger on the x-axis. Okay, and then they're going to keep growing. It's a rough sketch. Okay, you can mark these. Let's go ahead and mark them with the corresponding values. So z0 is equal to 0. That's the origin. This one is z0 is equal to 1. This one is 2. And here we get 3. Okay, so these curves are sitting 0, 1, 2, 3 units above the xy plane, right, correspondingly. Okay, all right. Let's take a look at one more example, and then we'll check all of these problems with a Wolfram-Alpha graph. Okay, what do we have here? Z is the square root of 25 minus x squared minus y squared. Okay, once again, you can make a note that z will have to be greater than or equal to 0 because we have a square root function. Okay, we go ahead and make a table. I'm going to be picky about what I'm going to select for my values because I know that I will be squaring each side. So now I'm going to pick values that make sense to me. So let's say 0, and then we'll do 1, and then I'm going to do square root of 5. I'm going to do square root of, let's say, 10 and square root of 15. Okay, because once I set them up, set them equal to my expression, okay, and squared, what do I get? Okay, so I get 0, and what do I get here is equal to 25 minus x squared minus y squared. Okay, then this one is 1 is equal to 25 minus x squared minus y squared, and so forth. I'm going to go ahead and square all of it. 5, this expression here, 10, and 15. Okay, and now once I isolate x and y, it will be clear what we get in here. So x squared minus y squared is equal to 25. Oops, sorry, this should be plus. Okay, and then x squared plus y squared. What do we get here? 25 minus 1, that's 24. And then x squared plus y squared is 20. And x squared plus y squared is what, 15. So you can see that my radius becomes smaller. As I pick larger values of z0, my radius becomes smaller, right? Okay, so these are all circles. They are circles centered at the origin, and the radius is the largest at z0 is equal to 0, and then as we're shifting it up, 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 the radius becomes smaller and smaller, right? So let's go ahead and make a sketch here. Okay, here's my xy plane. Okay, x plus y is equal to 25. That is a circle of radius 5. So That's my first one. Then x plus y squared, x squared plus y squared is 24. So that one has a smaller radius a little bit, but now we're inside, right? Okay. 20, then 15, and 10. Okay. So these are all getting smaller circles, right, as we go up. So this is z is equal to 0. This is z is equal to z null, right? Z null is equal to 1, and so forth. Let me go ahead and mark them all. Okay. This is root 5. This one is z null is root 10, and the last one is root 15. So you can see you can pick all sorts of different values, right? Sometimes we just kind of need to be careful what we pick. Okay, that's something that's in the range of the function to start with, right? And also sometimes you will just pick values that are convenient. Okay, so now you can visualize what's happening here. We start with the large curve at z is equal to null, and as we're going up, these circles definitely get smaller in radius. Okay, now I did graph all of these in advance. Okay, so here are the first two examples. Okay, if I go to Wolfram Alpha and just plug it in to the best of my ability, my equation would be something like z is equal to x minus y caret 2. Wolfram Alpha is pretty good about trying to guess what it is that you're trying to punch in, so don't worry about syntax too much, okay? But here what you see that they color code their contour maps. Okay, so here's your first example where we have this parabolic cylinder and our parabolas, okay, and you can see how they're shifted, right? So they're shifted, and of course they have different values that they pick, but the idea is the same, right? Okay, and they select what they select lighter color for larger values of z. Okay. Similarly, so here's your square root of x squared plus 4y squared. Then we have a contour map here where we have these ellipses. Okay, we have really dark ellipse in the middle, so that represents the smaller value of z, and then they get lighter and lighter. So that's that. And then the last one, here's your z is equal to 25 minus x squared minus y squared, square root of this expression, right? Okay. And this plot will actually give you two parts. You will get a real and imaginary part. That is, if we allow expression under the radical, take negative values, right? So in this class, we're not considering those options. Okay. But now you can see, oh yeah, so here's my really, really big circle on the outside that represents z is equal to 0. And that, of course, let me go ahead and kind of make a connection here. It represents this part, nope, that you can't tell. So like this part right here, where this dome is touching the xy plane, right? So that corresponds to this outer circle, right? Okay, so these are your contour maps or level curves. Both of those terms represent the same idea. Okay, so when working with these problems, let's say something on a quiz, on an exam, I would ask you to solve a problem of this flavor, okay, where you can easily plug in a couple of values, usually 4 or 5 level curves, and get curves that are very familiar to you. Okay, something simple as a parabola or a circle, an ellipse, something that you're very familiar with, and then we can sketch them, label them carefully, and then if you're working on a homework or a quiz, feel free to check your work with Wolfram Alpha. It's definitely a very useful tool to use. Okay, I think we will stop right here. In the next video for this chapter, I will discuss limits and continuity of functions of two variables. Thank you for watching.